on the physical properties as well as stabilities of alkenes. And then we'll move on to a more important topic, which is another type of reactions that you are going to see, which is actually making the alkenes through elimination reaction. So in terms of the physical properties, alkenes are similar to alkanes. If both are hydrocarbons, just by introduction of a double bond. And let's say if we look at the dipole moments, are usually small, ranging from 0 to 0.5 dBu. And so if you look at something such as ethylene, the dipole is 0. As you would expect, that even though our hydrogen bonds have a slight polarity, it's very, very small, and they kind of cancel each other because it's a symmetrical mode. Now, if you introduce a methyl group to one of the hydrogen, then there's a small dipole, such as about 0.3 dBu. Now, the question is, as we already have indicated, that the methyl groups are typically donating electrons towards the bond. And one way to address that is actually comparing some molecules, such as if you put a halogen, that makes it significantly more polar. So if you, let's say, change one of the hydrogen to chlorine, then the dipole moment becomes 1.4 dBu, which is quite significant because of the presence of the chlorine, which is extremely electronegative, as you can see from the electronegative scale. And now, if I replace this hydrogen with the methyl, then because it's donating in the same direction, the dipole actually increases. So if you add the becomes 1.7 dBu, okay, which is clearly calculated from the 0.3 dBu unit of the methyl group donating towards the bond, and then the chlorine is actually withdrawn. So it's in this direction. Yes?
In the previous molecule where we just replaced one hydrogen with a methyl group, what's the direction of the dipole there?
You are asking about this one?
Yeah.
Yes, this is also towards the double bond. That's the direction. And that's why it adds on. Otherwise it would have canceled, and it would be 1.1 rather than 1.7.
I mean the net dipole, so is that?
The net dipole is in the same direction. All right, so that's as far as we are going to discuss about the dipole. Now, in terms of the stability of the carbon-carbon double bond, the alkenes, as we know, have sp2 carbon. Therefore, they actually have a planar format, and the stability of the alkenes are also based on how they are oriented. So one of the things that happens is, like, let's say start from this. the more substituted a double bond would be with alkyl groups, the more stable that is going to be. So in other words, if you consider the alkene, and you can see that you can put one R group here, okay, which we'll call it monosubstituted double bond, because there's one alkyl group here. Followed by, let's say, disubstituted. And the disubstituted, of course, it would be either on the same molecule, same carbon, or a different carbon, also cis or trans. But we'll get to that in a couple minutes. Okay. There are other types also. And then trisubstituted and tetrasubstituted. In each case, it increases the stability. Stability goes in this direction. And that's essentially the thermodynamic stability of these groups of molecules. The more substituted it is, the more stable it is going to be.
Well,
the second issue is, of course, between cis and trans, or Z and E. In those cases also, typically what happens is the cis has this is a Z, and another molecule, let's say, call it E. And in those cases also, the stability actually goes in this direction. The E molecules are more stable because of less van der Waals interaction. Less van der Waals interaction between the substitute. And also that will depend on the size of the substitute. The larger it is, the difference would be more pronounced. And to give you an example, if we look at the stability of different alkenes, this is the pattern that we see. Let's start with a 4-carbon unit. So we have so this is monosubstituted. Right? Monosubstituted means you have 3 hydrogens and 1 is occupied with an alkene, in this case ethylene. So compare that with 2-butene, and 2-butene will have cis and trans. So 2-butene cis and 2-butene trans. And of course, you can also consider both groups are on the same carbon. And this is actually more compact. So the stability actually goes in this direction. The more stable would be in this direction. And how do you know that? One of the ways these are assessed is by doing the combustion analysis. In other words, you actually burn them down to carbon dioxide and water and see the heat released. And that can be measured. The heat released, even though they are all have the same molecular formula, is this is the lowest, followed by this one, next this one, and this is the has the highest heat of enthalpy release. So the stability again is predictable based on 2 things. One is that whether or not the double bond has more substitution, in this case a mono-substituted, these three are all di-substituted. And then the next thing to look at is the van der Waals interaction between the groups. If the bulky groups are on the same side, they'll have less stability. And again, if the molecule has more branching or less surface area, that also contributes towards the stability, as in this case, where both methyl groups are on the same carbon. So that's pretty much all we are going to talk about the stability as well as the physical property of these molecules, and we'll concentrate on the more important topic now. Any question? All right, so let's look at another type of reaction, how the alkenes are produced. So synthesis of alkenes. Now the commercial or industrial synthesis of alkenes, such as propene, can be done from propene, or ethene can be done from ethane or propane. So you eliminate a hydrogen from each of those two carbon units and generate a carbon-carbon double bond. Okay. So this process typically can be done in a variety of different ways. The industrial method is using a very high heat. And these type of reactions are called beta elimination. Or 1,2 elimination. Now the beta elimination can also be accomplished by other ways. In fact, in the laboratory, we don't use this method. If you are to make an alkene, these methods really needs very high heat, and therefore that is not very convenient to do that. We do it in a different way. You can use less heat, and one of the ways would be done, let's say, the same compound can be generated in the laboratory. Would be using ethanol. From ethanol, what you need to do is provide an acid such as sulfuric acid and heat it, and that is going to generate the So what was actually done here is to remove this OH group, okay, and one of the hydrogens from here. So that's why these are 1,2 elimination or beta elimination. Now what is beta? The Greek letter is given based on, in this case, this is alcohol. So this carbon to which the alcohol OH is attached is called alpha carbon. And the next carbon would be a beta carbon. And the elimination is beta. The reason it says that is that OH group takes away also a hydrogen from the beta carbon. And that's why it's beta elimination. And we'll see many examples of these. All right, so now this is just a most simple reaction in which you use ethanol to make the ethylene. But many other molecules can be used. Let's say cyclohexanol. Under the same condition, you use sulfuric acid and heat. That is also going to generate a molecule of water and cyclohexene. And of course, you can predict many products like that. If you start with tertiary butanol, you get make this plus H2O. So So these are all examples of beta elimination reaction. All right, now, what happens if you have other substituent in the molecule? How that is going to influence? Because in all the cases so far we have described, only one product is possible. But there would be cases where more than one product would be possible, right? And let's just give you an example of that. Let's say in this case, rather than having cyclohexanol, you have 2-methylcyclohexanol. And now you can see that there are 2 products possible from this one, because the 2 beta carbons, okay, from which the hydrogen would be abstracted are not identical. In this case, this is the alpha carbon, this is a beta carbon, and this is also a beta carbon. Now, therefore, that gives you 2 completely different products. One product would be where the methyl group is, and another product would be this one. So 2 different products that are possible, and of course their names are different. They are actually 2 completely different compounds. And would you expect equally this to produce? Okay. And that brings us to a Russian chemist named Zaitsev, who suggested that no, this is going to be coming most from the product where you have the carbon with the least number of hydrogens. So this is called Zaitsev rule. According to this rule, the hydrogen will be taken out from the carbon with least number of hydrogens. Now, based on that, we looked at both beta carbons and which has the least number of hydrogens.
OH.
The one with the methyl group, right? Because of the presence of the methyl group, you have 1 hydrogen there and 2 hydrogens here. So according to Zaitsev rule, this would be the main product. So this is the major product. And the other one would be minor product. And we can never exactly predict how much, but we can definitely predict which one would be the main product. In some cases, it's 90% and 10%. In some cases, it's 80% and 20%. But nevertheless, we don't know the numbers, but we can predict what the major product would be. All right, so we'll provide the basis for the Zaitsev rule later, but let's look at some of the other compounds and try to see that how predictable this type of reactions are. So whenever you are looking at this type of elimination, what you need to do is go to the alpha carbon and then see how many beta carbons are there. If you have multiple beta carbons, then figure out which one would give you the major product. Because it's for your exams, it's very important for you to recognize that. If you write all the products, you may get partial credit. But to get the full credit, you need to indicate which one would be the major product. Now tell me which one would be the major product from this. Because this one can give you also different products. One product, as you would expect, is these two carbons are almost identical, so it will give you this. Right? The second product that is possible is this. Because you have a beta carbon here, a beta carbon here, and a beta carbon here. Now, according to Saint-Cyr rule, which one would be the higher amount? Which would be the major product? The first one or second one?
Second one.
Second, right. So this is the major product. So following the Saint-Cyr rule is quite very easy. You just count the number of hydrogens. Here you have 2 hydrogens. Here also you have 2 hydrogens. But this one has 1 hydrogen, and therefore the major product comes from that. Now, in addition to that, there is also the stereochemistry. Whenever the stereochemistry is involved, and not all cases will involve stereochemistry. If you have a possibility of generating a more crowded product or a less crowded product, typically, as you would predict, the product would have less crowded structure. So, give me an example here, such as propanediol. So now, in this case, even though the beta carbon would essentially generate the same product from either one, okay? And the Saint-Cyr rule doesn't really apply because it's only giving you one product. But you can generate 2 geometrical isomers from that. And the geometrical isomers would be, let's say in one case, you will have
What is for the first one on the top? Is it the same hydrogen sulfate need?
What?
Major and minor for this double cyclohexyl is the
yeah, this is that there are 3 beta carbons, right?
so the heat and the hydrogen sulfate.
The major product comes from this one because this one has 1 hydrogen.
No, that's not what I'm talking about. I'm talking about like is it heat that you use to make the major and minor product? Like when you use the purity.
But you need to add heat and hydrogen.
Oh yeah, of course. I didn't write that. You need to provide the acid and the heat. Otherwise, the reaction will not. Yeah. It's the same condition. That's why I mentioned that. Yeah. Okay. So, all right. So in this case, you can get a Z isomer, as in this case, or an E isomer, where the methyl and the ethyl group will be on the different side. Now, because of steric hindrance, the van der Waals interaction, the E product is thermodynamically more stable, and therefore that's the product we also get there. Major product is coming from that. Okay, now let's discuss how this reaction really proceeds. And I'll start with one example and go over that in a couple of minutes. And you will see the similarity between this and what you learned from chapter 4. Any question after this one? All right, so let's see how this reaction really proceeds. And let's start with like cyclohexanol. So step 1 of this process really involves again a hydrogen transfer. It's exactly identical to what we have learned before in chapter 4 when we were looking at the SN1 and SN2 reaction. So the oxygen essentially picks up the proton from sulfuric acid, giving you step 1 of this process. In the second step, again, it is following exactly the same way as we have learned in the substitution reaction, that you need to break this bond between oxygen and the carbon, making a carbocation. So step 2 is the slowest step. This is slow, and therefore rate determining step, RDS, which breaks the bond between the oxygen and the carbon, giving you H2O plus HSO4 minus. Now, what is different now is the third step. You remember this part was exactly the same as we have seen in substitution reaction. But in the substitution, you had a nucleophile present that was going to attack the carbocation and form a new product. In this case, there is really no good nucleophile present. So what happens is the water molecule can pick up one of the proton acting as a base. Step 3, which is relatively fast, and generates the alkene. So again, if you remember the previous one in SN1 process, rather than SN1, this is an E1 process, or elimination unimolecular. And so the rate curves are also kind of similar in the way that you first get from the attachment of the alcohol, you get a protonation first, which then goes to a second step, which has a high energy barrier to generate the carbocation, and the third step again is quick. So we can draw that pretty much the same way, that you have OH plus H2SO4. Relatively quick reaction, protonating this species. Then the second step is large activation energy, where you generate.
Can you bring up the paper a little bit? Thanks.
Second step has a large activation energy barrier, generating the carbocation plus H2O plus HSO4 minus. And the third step giving you the alkene. So this is the energy of activation 2, which is the highest. So the pattern is very similar to what we have seen, except the third step, which is different. Okay. And as we'll see later on, that the substitution and elimination can be competing reactions. Okay. Sometimes when you have a nucleophile present in there, whether the nucleophile is going to attack the carbocation or the other base will pull out the proton, there is a competition between them. And you may get both products depending on the conditions. And we'll describe that later and go over that. But again, we are introducing now to a new elimination reaction, which essentially follows a very similar pathway as we have seen in the case of substitution. Any questions?
drawn that final energy level there, is that supposed to be lower than the initial state or
It could be higher than the initial state, this stage, little bit higher because you generate an alkene, which is less stable than an alkane. Okay. And we'll also talk about more about the transition state. That is very critical. Okay, now, before I return your quiz, I want to mention a couple things to you. The second exam is going to be significantly harder than the first exam. I know a lot of people who got 90s feel very comfortable, and I don't really want to panic you, but a lot of people who have got 90s will get 60s in the next exam.
What if you got 60s?
That's easy. The material gets more difficult only if you do a lot of problems and understand the material better, you'll do well. So you have to stay with it, try as hard as you can. Because next chapter, next exam will include chapter 3, 4, and most of 5. Okay? And therefore, there are a lot of different concepts introduced, the reaction as well as the potential energy diagram and so on. I'm going to give you a practice exam today, which I would ask you to try, not before you have tried some of the problems that I already assigned. Try the homework problems that I assigned. Do them first, feel comfortable about the material, and then try the problem. Okay? So when I return you the quizzes, pick up one of the